Okay, so we're in Chapter 4, Section 6 now, and this section is about precipitation reactions. So we've set ourselves up nicely to understand this. Let me tell you at the outset that this conversation is going to be much more pleasant if you go and pull out, look at this here, if you go and pull out your solubility, so table 4.1, take that out of your notebook and look at it while we're talking. This conversation is going to be much more accessible. It's a little bit abstract if you don't do that. Okay, so how to predict precipitation reactions. Very important. So first of all, let me remind you about the table. What I've got on my computer is the table is pulled out as a PDF, as a separate one, but remember now what this means. This means that, sorry for the background noise, I asked someone's making a cup of coffee for me here, and so, all right, so remember what this means, right? That if you have lithium in a compound, it's generally going to be soluble, except when it's compounded with, well, nothing, right? There's no exceptions for lithium. Okay, thank you for the coffee. That's what this table means. Let's look at another one. Ammonium is generally soluble, except when it's compounded. Well, there's no exceptions, right? So ammonium anything. Ammonium has got a plus on it, so suppose we put it together with something that had a minus on it. Oops, that's ammonium. This would be soluble, right? And if we put this in water, it would be ammonium X. It would be aqueous. It would be dissolved. Okay? So that's what this table means. Nitrate. Oh, again, you might want to pull out table 3.4. Again, I could not overemphasize, honestly, that if you're looking at these names and you're calling them by name while you're doing it, you're going to be much more comfortable. Very important. I hope I can persuade you to do it. So nitrate, right? So when nitrate is compounded with something positive, let's say potassium, right? Well, anything. I'm going to say X. It's got a positive on it. If I put this in water, no matter what, it's going to be aqueous, right? Because there are no exceptions. That's not the case for iodine or iodide, right? Let's take iodide. It's got a minus on it. I want to put it with something else. Let's take one of these guys. How about silver? If we put this in water, right, we find that iodide is generally soluble. I realize I'm destroying this table here. Iodide is generally soluble. However, when it's with silver 1, which we don't say silver 1 because silver is always 1, silver, when it's with silver, it's not going to be aqueous. It's not going to dissolve. Okay? And the same thing for mercury 1 or lead 2. Did you hear me call that mercury 1? Why did I do that? Mercury 1? Okay, yes, that is mercury 1. Why? You know why. You've been given the rules a couple times, but surely it's still a little bit scary. So go back and look at the rules of why we call those things what we call them. That is mercury 1. All right, so that's what this table is all about. This up here, these were the compounds that were generally, or the ions that make compounds that are generally soluble, okay? But look down here, here's the ones that are generally insoluble. Let me change colors here. Pen color, let me go to blue. These are generally insoluble here, right? So if you have something sulfide, this is probably not going to be soluble, right? So how do we know? Well, we look over here and we say, it looks like calcium sulfide. Calcium's always got a 2+ on it because it's group 1, or rather it's group 2. And sulfide always has a -2 on it. Sulfide does because as an ion, it's in group 6. Okay, so this is the formula for calcium sulfide. I suggest that you take time as you're doing these videos and write these names out instead of just getting swept along like I did when I was a student. I just got swept along, started figuring I'd get it later, and I just never did. So calcium sulfide, that looks like that's going to, if we put this in water, wait, oh, look at that. So it looks like that's going to be soluble, okay? So we've done this table a couple times before, but I wanted to remind you what it looks like. We need it. So let's go on now and talk about predicting precipitation reactions. Do you have a definition of a precipitation reaction? Let me pull that up. I gotta pull that up. You know what? I'm not even gonna pause the video. I'm just gonna go grab my book. Should have had it with me. Be right back. Don't go anywhere. Okay, I'm back. I'm looking up precipitation reaction. You want to do this. You want to look it up. And if you don't know where it is, and I'm expecting sort of that you don't, right, because you're not the professor, you want to look it up in the index. I'm the professor. Oh, you would know where it was. What am I talking about? We're in section 4.6. We're looking at section 4.6, aren't we? So the definition of a precipitation reaction is on page 149. And a precipitation reaction, go back to red here. Oh, red now. A precipitation doesn't really belong in this slide, but I'm going to put it here anyway. A precipitation reaction is, looking at for a definition here, it is I'm looking for a pure definition. Just one moment here. Well, it's in bold, so it's described on page 149, but the looking for our examples of okay, yeah. Okay, here it is, page 149, right by the, of course, right by the bold print, right? So it says a precipitation reaction. They are reactions in which a solid or precipitate forms upon mixing, watch this now, two solutions. Okay? Please stop and look at that reaction. Please stop and look at page 149. Okay, look at the definitions. It's just really important that you're relaxed when you're doing this, okay? So, do you see a solution here? Sure. This is a potassium iodide solution. Please pause the video and name this. Pause the video and name this compound. Okay? I'm going to pretend that you did, and I am going to do what you should have done. You're going to look at this and you're going to say, okay, this is on table 3.4. If you didn't look there, please pause the video again and look at it. Table 3.4. I look up NO3, and it shows up as NO3 minus, and its name is nitrate. Okay? So if there's two of them, it's 2 minus, right? Well, each of those only has 1, okay? So be careful. I'm not sure what this little notation means to you. Let me get rid of that. Let me put a -1 and another -1 because there's 2 of them, right? So that must mean that this must be lead +2, and lead is a transition metal, so it's going to be lead 2 nitrate. Do not waste opportunities like this to practice your nomenclature. It's win-win. All right, so we have 2 solutions here. One of potassium iodide, which we're going to call this aqueous, potassium iodide, and this is going to be called, right, aqueous lead 2 nitrate. Okay, so when we've got these two aqueous solutions, are we going to get a precipitation reaction? Are we going to get a precipitation? Look at this. A precipitation reaction is when there are reactions in which a solid or precipitate forms upon mixing two solutions. Well, we know potassium iodide is soluble in water because, let me go here. Look at this here. Potassium iodide is soluble in water because, can you see this? Because potassium is here, right? And there's no exceptions. So potassium iodide is generally soluble with no exceptions. So potassium iodide is soluble in water. We also know that because it says aqueous, right? What about lead nitrate? Lead 2 nitrate. Is that soluble in water? Oops, I lost my notes. Lead 2 nitrate. Is that soluble in water? Well, yes, because it says aqueous. Look at that right there. You see it? So you might think, well, lead, that's probably not soluble. But no, look it says aqueous, okay? Well, let's go back over to the table. And the table says that nitrates, can you see that? Nitrates are generally soluble, except none. Look at that, except none. So that's why it's soluble in water, okay? Now that we know that, those are soluble in water, what might happen here? Let me go back and make some notes now. Well, we know that the potassium is now mixed. If we mix them together, my next slide is going to show this. It's going to be mixed in with lead 2 and iodide and nitrate. My next slide is going to show this, okay? So potassium and iodide are not going to make a compound. They're not going, because we already know that they're not soluble, or rather that they are soluble, right? That they don't precipitate. But potassium and nitrate, they might precipitate. So we go back at the table and we see nitrates are soluble with no exceptions. So no, this is not going to precipitate. And what about lead and iodide? Is lead going to react with iodide and make a solid? Is this going to happen? Lead and iodide, it looks like it would take 2 of those, right? Lead 2 iodide, because it's lead 2, right? Is that going to happen? Well, let's go back to the table. I'm going to lose all my notes when I go off this slide, okay? Just bear with me. Is that going to happen? Lead 2 iodide. So we go back here, and we go here, and we say, wait a second. Iodides are generally soluble, except when they are paired with lead 2 and mercury 1 and silver, right? Okay, so let's go back here and let's look now. Let's walk through this, okay? So again, you've got these 2 solutions. You see a solution of potassium iodide and a solution of, say it, please say it, lead 2 nitrate. Okay, we mix them together. Okay? Now that we've mixed them together, we say to ourselves, is the potassium going to bond or make, it's not really a bond, okay? So if you're a chemist and you're listening to me, don't complain, please. Is potassium going to bond with iodide? Then the answer is no, because no potassium compounds are going to precipitate. They're all soluble, okay? What about lead and, what about potassium and nitrate? No, because no potassium compounds are going to precipitate. They're all soluble, okay? What about lead 2 and nitrate? Are they going to bond? No, because that's how it came in. It was aqueous when it came in, right? But now what about lead 2 and iodide? We just agreed that was going to precipitate. right? This is not soluble. So when those guys see each other in solution, they say, hey, let's get out of here. Okay? Let's go on. So another picture of it. You saw we had the potassium iodide, right, and the lead 2 nitrate. We put them together. After we mix them together, the lead 2s, which I think were yellow, and the iodides, which were purple, they stack on top of each other, and they, watch this now, precipitate. That's what they do, okay? And when you say you have a precipitate, you say you have a solid. Now, you've seen this reaction before. We did it in lab last week. Okay, does that look familiar? So we must have had either, looks like here we had lead nitrate down here, and up here we were pouring in potassium iodide. That's what this picture says, and we get a precipitate. So this picture is also on page 149. Page 149. And if this doesn't make sense, I encourage you to go back and read it. You know, maybe watch the video again or go back and read the book. But it is something that is accessible to you. You can get this. Okay, so let's go on. Let's talk about, oh yeah, we already looked at this. So with potassium and iodide came in together, really should put potassium and iodide, and this was lead 2 and 2 nitrates. This is really like nitrate and a nitrate. Did you know that? Hopefully you knew that. You've been told. So 2 nitrates, are these guys going to precipitate? No, but these guys might, right? Because potassium brought in, introduced to the party, iodide, where lead might say, hey, let's dance, okay? So, and that's exactly what happens. This becomes a solid, and this stays in solution. Okay? Having said that, I think you've already seen this picture from another vantage point, like the big mixture we showed a little bit ago. The potassiums and the iodide, and the potassiums and the nitrates, they stay in solution, right? But the lead iodide precipitates out. Precipitate. Okay? So let's do a problem now. Write an equation for the precipitation reactions, for the precipitation reaction that occurs, if any, when solutions of potassium carbonate. This is where your nomenclature is very important. Take your time. Go back and pull out table. I think it's 3.4, but the one that names these guys, right? Potassium carbonate. Potassium's this. Carbonate is CO3 minus minus. So there must be, potassium carbonate must have 2 CO3, right? And nickel 2 chloride. Well, now it's easier when we're going the other way, because nickel 2, you know there's a +2 charge on that, right? In chloride, there's a -1, so there must be 2 of these, okay? So nickel 2 chloride. You know what? Let's do it in the order that it's given to us here, okay? Let's say when solutions of, and this, if it's a solution, that means it's aqueous. Potassium carbonate, aqueous, plus nickel 2 chloride, aqueous, produces, and you know for sure that the potassium is not going to precipitate with the carbonate, because we're told here, right here, it's aqueous, right? But the potassium, and it's not going to precipitate with nickel, because nickel's positive. It's a metal, right? But it could precipitate with that. So let's go, okay, Cl, and this is a +1, and this is a -1, chlorines are, so this is just going to be a 1-to-1 ratio, right? We'll decide in a second if that's going to precipitate. Now, it's possible that the nickel and the carbonate would go together. Nickel is +2, because it says nickel 2, right? And carbonate is -1, because that's what carbonate is. Or rather, -2, because carbonate is -2. So those will also go a 1-to-1 ratio, right? So I'm going to put parentheses here, and we'll fill those in a second. Now this is not balanced yet. Looks like there's 2. Those have to be 2. right? Can you see those? There's only one carbonate over here, and so one carbonate. So this looks like this is balanced. Now we have to decide if potassium chloride is going to precipitate. You know what? Every time I pull out a PowerPoint when I'm doing this, I lose my notes, and I don't want to do that right now. So I'm going to ask you to look at table 4.1. You've got it in front of you. I know you do because you are cooperative. So potassium, you see, according to the top line, I think it is, potassium's net top line, has no exceptions. It's always soluble. So this is going to be aqueous. What about nickel carbonate? So we look down at, you know what, I don't have table 4.1 in front of me, but I'm going to pull it up. You've got it. If you look in TRO, it's on page. If you look on TRO, it's in page 147, and you see in the very bottom row, carbonates are generally insoluble, except when they're paired with lithium, sodium, potassium, or ammonium, of course, right? Look at the top row, they'll say those are always soluble. So potassium, or rather carbonate, when it's with nickel, oh, that's definitely going to be insoluble, right? So this is going to be a solid. Aha, here's our precipitate. Okay, now let me look back up here and see if I've answered this question. Write an equation for the precipitation reaction that occurs, if any, when solutions, there's a solution of potassium carbonate and nickel 2 chloride, and that's nickel 2 chloride, reacts with, or rather, when they react together, right, when they're mixed. So we already figured out that potassium's going to have to dance with chloride, and nickel's going to have to dance with carbonate. Turns out these guys don't dance, they're still in solution. But nickel 2 carbonate don't miss out on the opportunity to name these guys. You'll thank me, honestly you will. You're gonna do more than thank me. You're gonna name your first 3 children after me. Because you're gonna say, you know what? Life got easy when I started practicing with Dr. Carbonate. Alright, so that's the answer for 410. I think that might be, no, we've got one more example to do here before this video is over. So let's go on to the next one, 411. Write an equation for the precipitation reaction that occurs, if any, when sodium nitrate and lithium sulfate are mixed. So, alright, so again, it's solutions. It means they're aqueous, okay? So sodium nitrate, I look it up in table 3.4. Okay, nitrate's got a -1 on it, sodium's got a +1, so this is so this is the correct excuse me, formula for sodium nitrate, and it's aqueous plus lithium sulfate. Well, lithium, I'm going to look this up. Lithium is +1 because I look on that table, or because it's in group 1, either way. And sulfate, I have to look this up. It's in table 3.4, and it's SO4 minus. Okay, so if we have 1 plus and 2 minuses, it must be lithium 2. I'm sorry, not lithium 2. It's just lithium sulfate. Right, but there's a sub 2 there. Okay, and we know it's aqueous because it's a solution. Okay, so if these guys precipitate, then it's going to be sodium. Not with lithium because that's a metal. Sodium is going to go out with sulfate, or nitrate is going to go out with lithium. Right? So let's do this. I'm going to write these out. Sodium, and it's a +1, and sulfate is -2. So it's going to take 2 of those to pair up with sodium sulfate. And we'll see what the state is in just a moment. And now we have lithium, and lithium is a +1 because it's in group 1, and nitrate is a -1 because that's what nitrate is, according to table 3.4. Lithium nitrate, right? So they're going to go 1 to 1, and we'll look up the state in just a moment. Let's balance this before we go any further. There's 2 lithiums here, so there must be 2 here. There's 2 nitrates now. There's only 1 over here, so there must be 1 here. There's 2 sodiums, and there's 2 sodiums here. And so I think that's, it's definitely balanced. All right, so let's look up the states in table 4.1, the states of these. And we know that all sodium, according to the top row, look at the top row. What's it say about sodium? No exceptions. This is not going to precipitate. It's going to be aqueous. And lithium is also in that top row. And nitrate is in the next row. No exceptions. Okay? So we do not have a precipitate. No precipitate. And Trove recommends that you write out here, no reaction. Okay? All right. I think that's. I think I said that relatively clearly, although I admit that it is difficult for a lot of students. So please consider reading the book, doing these problems independently, and going back and watching the video again. Try to understand this before you get to class, so we can just iron out the details when we get there. Okay? Best wishes.